And so the third talk we got this morning is Ryland, Degnan of Netifi. If the way I think about their technology, oversimplifying slightly, is they were in essence reinventing congestion control, but now at a layer 7, right? By moving to message-based protocol that no longer has a direct connection between sender and recipient. So all the control mechanisms that we had previously no longer work. So it's time to invent something new. Ryland?
Great. Thank you, Guido. So I'm Ryland Degnan. I'm the CTO and co-founder of Netifi. Prior to that, I was on the Netflix Edge platform team that created this RSocket protocol. So I'm really excited to talk today about RSocket, what it is, what problems it solves, and why I think it's the future of cloud networking. So communication in the cloud is a challenge. And I've had firsthand experience of this. If you think of Netflix as sort of a giant hourglass with all of the different browsers and devices, set-top boxes that we supported on the top, and sort of 10% of North America's upstream traffic funneling in, and then all of the hundreds of microservices within the Netflix ecosystem underneath. Our team sat right in the middle of that funnel. And so I've been paged in the middle of the night and had to go in and scale up and scale down services to try to coax this system that was on the verge of failure back to life. So I've dealt firsthand with a lot of these challenges. And I think enterprises today are in this transition state between the world of the data center, sort of the monolithic application in a very controlled environment, to this Wild West environment of the cloud, where suddenly there's all these different deployment topologies and platforms that we need to be aware of and consider. And that causes a problem when you try to take sort of the same networking abstractions that worked in the data center and make a one-to-one translation to the cloud. And there's growing awareness of these problems. So these quotes are from a recent Cloud Native Compute Foundation conference. The network is the unsolved problem of cloud. We need the network to be a first-class citizen. We need a standard approach to connecting and communicating microservices sort of across our application. And so this is the purpose of RSocket, is to simplify and standardize this communication, no matter what infrastructure you're running. And as I said, it started as a Netflix open source project. It now has contributors from Facebook. It's being used at Facebook, Pivotal, and my company, Netifi. And as I said, the purpose is to provide a single unified API for communication, regardless of what transport you're using, regardless of where your application is deployed or what topology you're using. And it's also built to solve the cross-cutting concerns of modern cloud applications. So in addition to the flexibility in the transport layer, there are problems like a reliable network abstraction, having resumability built into your protocol on the application layer. And things like flow control, predictive load balancing to let you plug the different pieces of your application together and have them just seamlessly work without having to reinvent the wheel at every step. So I want to look a bit more deeply into so what is a modern cloud application? What makes it fundamentally different than things that have come before? So firstly, almost by definition, it's distributed and it's heterogeneous and it's interactive to a degree that we haven't seen before. I think a common mistake people make is to think of applications purely in terms of the back-end infrastructure. But that's certainly no longer true. I mean, today's users are distributed geographically all around the world, and we have our application infrastructure needs to be distributed geographically to match that. And it's not just geographical, we're also pushing compute to different layers in this stack, so all the way up to users' mobile devices, which are now more powerful than ever, or web browsers, which are essentially modern application servers, or incredibly powerful set-top boxes or gaming consoles. So they're increasingly different topologies that we can take advantage of to move compute around the system. And then inevitably, there's an explosion in devices, IoT devices, browsers, mobile phones, set-top boxes, my developers' laptops, or servers in my data center. And so any abstraction that intends to simplify communication really needs to work across all of those things. I think another way of putting this is there's this explosion of complexity, and it's not just along one axis, there's sort of multiple axes going on. I think broadly they can be categorized like this. So one axis is the sort of deployment topology where your code gets executed. And another axis is the platform or framework that your code is sitting on top of, whether that's Kubernetes or AWS Lambda or Tomcat and data center. And then the third axis are these different protocols and interaction models that we're using. So increasingly moving away from the sort of monolithic server and thin client to this network of nodes within a cluster that are interacting in a much more complicated way with one another. And so to dig into each of those in a little bit more detail, deployment topologies. As I said, in addition to geographical distribution, there's all this sorts of stuff going on. So there's hybrid cloud, multi-cloud, private cloud, and data center all sort of going on at the same time, and all with their place for different parts of your application. And increasingly, people are using not just one cloud, but sort of spanning their services across multiple clouds, and there's very good reasons to do that. And then on top of this sort of explosion in possible deployment topologies, there's also this explosion of platforms or frameworks or orchestration platforms that you layer on top of that. So typically, I might want to run some of my code as Lambda functions. Others I might want to deploy to Nomad and AWS. I might have some legacy application I'm moving to the cloud. I want to containerize that and put that in Kubernetes. And I want all of these things to interact with each other. And so that's part of the challenge of providing a communication abstraction that works across all those boundaries. And lastly, the different protocols and interaction models that all have to coexist within a modern cloud application. So there's still a place for the sort of client-server modality. So I might have a web page that's being served by Node. It's being sort of requested by a web browser. It's a request-response model, and that might be, in turn, requesting some information from a traditional database. So we call that sort of the request-reply interaction model. But on top of that, there's streaming interaction models going on. So my users, as they interact with my application, are generating a stream of data that I would like to use. And so it's streaming that data, ingesting that data into a data pipeline, and then retrieving it later, doing some processing on it, or increasingly writing real-time streaming algorithms that can understand things that are going on in my system in real time and react to them. So certainly, streaming interaction models have a huge place in modern cloud applications. And then the third one is sort of the RPC style interaction model, so using something like GRPC. And my concerns here might be more like lower latency, and this might lead me to use protocols like InfiniBand or Aeron if they're available sort of within my data center or within my slightly more controlled environment of the cloud. But all these protocols, all these interaction models have different implementations of, say, security, load balancing, flow control. And so rather than having to reinvent the wheel at every step along the way, I want some sort of overarching abstraction that's exposed to the application layer. And then on top of that, there's sort of emerging real-time protocols or peer-to-peer protocols, because maybe I don't want requests to go all the way back to my data center to have to go all the way back out to another user. I really want to enable some kind of peer-to-peer or real-time interaction between them. Or I want my mobile users to have a persistent connection that reaches in and is able to respond in real time to things that are happening within my application. So can we do something about this mess? I mean, if you take a look at it, it's ridiculous, right? Like, do we really have to piece all these things together for every application that we build? The good news is there's a relatively small and finite set of interaction models that sort of constitute the entirety of the things that we want to do in this system. And so that gives us a jumping off point to try to standardize on that and model them. The bad news is the current state of the art is within this three-dimensional space of complexity, any point you choose in that space essentially requires you to rewrite your entire application. So I can't just, as we found out, write an application that runs in AWS, say I'm going to use Java for everything, my database is going to be SQL. I can't one day go out and switch that to run in Azure, switch everything to Node, use WebSocket everywhere without rewriting my entire application. And so if we look into what we can and can't do, there's things we can't do anything about. And one is the deployment topology. I mean, it's tempting to say, we can construct the world in such a way that everything exists within a walled garden of infrastructure. But that typically doesn't turn out very well. I can say I'm going to write my entire application in Google Cloud. I'm going to use Ruby for everything. I'm going to use this one database as my preferred database, and everything's going to be great. And that works out well until you're paying Google $1 billion a year for their infrastructure. You're running into scaling problems that you can't deal with, but you're locked into the initial choices that you made in writing your application. And you have no way out other than rewriting the entire thing. And nor would we want to, really, because we want to be open to new technologies, and part of the beauty of the cloud is that it allows you to take advantage of new technologies as they come along. So if a developer wants to write a backend for a service in Node because it makes a lot more sense to him as a front-end developer to write his backend in the same language, that's fantastic, and we should enable him to be able to do that instead of trying to lock him into a certain framework that's pre-approved. But there is something we can do something about, and that's take this small set of interaction models and try to define a standard that lets you implement things that you care about within your system once using a single standard, so they don't have to be implemented and re-implemented again and again for every application, for every interaction model. And that is really what RSocket is all about. So RSocket simplifies communication. So it takes these different interaction models and provides a very simple interface that allows you to implement these different interaction models once. And this interface is in Java, but it looks very much the same in any language, C++ or JavaScript. And it builds in things into the protocol like flow control. So the types that are exposed here are reactive streams types that lift flow control to the application layer and allow you to plug together these things and do sort of things like fan out and fan in, and have flow control propagate naturally through the application layer to downstream applications, no matter what underlying transport you're using, whether it's WebSocket or Aeron or TCP. And so RSocket gives you a way to solve problems you care about in a consistent way across your application without making any assumptions about the infrastructure, language, or framework you're using. And having standardized on this common network abstraction, it means everything is suddenly pluggable. I can switch my cloud provider without changing a line of code. I can switch orchestration platforms. I can switch transports because Azure suddenly supports InfiniBand, and none of my developers have to care, and they don't have to change a line of code. So how does this work? So to construct an RSocket, essentially you choose a transport and plug it in. And the transport needs to have certain characteristics. It needs to be sort of a bidirectional, connection-oriented transport, but there's several that fit the bill. And so it's as simple as saying, if I know there's a service available to me at some IP address, I can connect to it. I can choose to use a TCP transport. Perfect. And what's returned to me is an RSocket. It's the interface you saw before, which suddenly enables all these different interaction models. And the beauty of this is that depending on, I can later decide to construct this RSocket in a totally different way. I can change where it's connecting. I can change the protocol it's connecting over. I can change things that it's doing behind the scenes, sort of enabling reconnection logic, retry logic. And nothing ever changes about the interface that's exposed. So having worked with this a lot at Netflix and at Netifi, we started to see it's what RSocket really allows you to do is to take this abstraction and leverage it to provide layers and layers of more abstraction. So if you look at the first code snippet, it's still sort of implying that you exist in an infrastructure, because there's certain things that I need to know about the service that I'm talking to. For instance, how do I get this IP address? Well, that implies that there's some sort of service discovery. So I'm querying a list of IP addresses, and then somehow constructing a load balancer or choosing one at random to connect to. But then where that brings us back to the level of having to re-implement this logic with every application in every language. But it's possible to use RSocket to avoid having to do that. And so that's what we've done with our Proteus technology. Proteus allows you to say, I don't care about IP addresses. I don't really, as a developer, I don't ever want to even know what an IP address is. I want to connect to a service. And I don't care whether that service is implemented in the data center. I don't care whether it's running on AWS. I don't care whether it's running in my user's web browser. It shouldn't matter to me. So using Proteus, I can say, I want to talk to some service foo. And what's handed back to me is an RSocket, exactly the same as the RSocket that I had got where I could to connect directly to this service. And there's more things you can layer in. So it's not just about routing. Proteus leverages the flow control of RSocket to create sort of these distributed load balancing algorithms that take flow control into account. And that lets you do really cool things. So I can run half my service in Google Cloud. I can run the other half in Azure. And depending on where users connect into the network, it's going to be routed to one or the other. And I don't have to configure a thing. It's constantly seeking to optimize for the lowest latency path to available services. And on top of that, it's got things like built-in monitoring that I get essentially for free without having to change that on every client. And it does all this without making any assumptions about my infrastructure, meaning I don't have to install it along with an agent or sidecar. I can use this same technology in the data center or the web browser or my laptop, and there's no sort of infrastructure that has to exist for me to be able to take advantage of it. So how does this work? So Proteus is essentially trying to achieve the equivalent of being a TCP router, but not for IP addresses, for services. And so what it does is you deploy this network of Proteus nodes, they discover one another, cluster together, and then you connect into it from anywhere. So I could connect into Proteus from my web browser, another user could connect from a mobile phone, they can offer services to one another, and suddenly they can have peer-to-peer communications with each other. And they might be sending a few bytes of JSON, or they might be sending a gigabyte, image file between them. But both of those are perfectly acceptable in RSocket. It's got built-in chunking and reconstitution of the payload such that it presents this network abstraction that lets me say, I've just received a gigabyte long file, and I don't care actually how it got there. In addition to that, I can start to plug in my backend services. So I might be running a service in C++ in my data center. I can plug that in, and suddenly it's available to everybody else within this network. And tomorrow, I can re-implement that same application in Node if I deem that appropriate. And nobody who's using that service ever needs to know the difference. And the other cool thing is it doesn't matter in what order things connect, because it takes advantage of RSocket back pressure. I can have a browser connect in and start requesting a service that's implemented in Node before that Node server is even started. And because of back pressure, and because of Proteus is aware of the presence of things within the network, no traffic will ever start to flow until that traffic is able to be fulfilled. So if my system is getting overloaded, the traffic will naturally slow down, and that back pressure gets propagated all the way to the originator of the request and forces it to say, hold on a second, we don't have enough capacity within the system right now to fulfill your request, so decide what to do with it. Either if it's important, hold on to it for later, or if it's not, you can drop it. And it's not just about services, so I can start to plug in things like open tracing if I want to get insights into what's going on within this network of services. And the cool thing about this is I can just plug this in, and I just start to get tracing information without changing anything. And that's by virtue of the fact, as I said, every Proteus client is constantly seeking to provide tracing information, but if there's nothing to ingest that tracing information, nothing will ever happen to it, it'll just get dropped. So the entire system is sort of constantly ready to provide information, and it's up to you to plug in any backend tracing implementation, any metrics backend that you like. And then that's also available to be sort of queried later on. And all of this is essentially done without configuration. So it's really geared to be more like a TCP router, where you might set it up once, and then it's really invisible to a developer from then on. They don't have to worry about it. It's part of the fabric of the network. And this is opposed to something like Istio, not to knock Istio, but this is sort of symptomatic of any approach to solve these problems on the infrastructural layer. And we ran into the same problems at Netflix. There's this explosion of configuration and tuning that has to go along with this approach. So for instance, tuning of circuit breakers. Within Netflix, every time I scale up or scale down a service, I need to revisit the circuit breaker parameters that I had set, or else I won't be sort of getting the maximum out of my system. I might be tripping circuits too early or allowing too much traffic to flow in. And this is a constantly changing thing that requires me to go back and revisit again and again and again, unless it's handled automatically. So as I said, Proteus leverages RSocket to provide a platform for modern cloud applications. It's a platform that works anywhere, that makes no assumption about infrastructure, languages, or framework. And it's built to make cloud applications simple. And it's a great example of the sort of system that RSocket allows you to build, providing this base level of abstraction. And that's why I think RSocket is so cool and really the future of communication in the cloud. So with that, I think I'm over time, so I'll stop there. Thank you.
Super, so we have time for a few questions. Who wants a microphone thrown at them?
Yeah, got it. If I were dropped on the planet just this morning, and everything I knew about Istio, and everything I knew about RSocket and Proteus were what I have just heard from being seated here, I would come away with the conclusion that you just disproved the need for a convoluted service mesh architecture. Is that what you just said?
I'd say the service mesh has its place, but I think its sweet spot is taking legacy applications, as you said, that you don't want to open that can of worms. You just want to sort of layer infrastructure on top of it. And I think it has its place in that respect. But I think for new things, in order to really take advantage of the cloud, tying yourself to a deployment architecture, like forcing yourself to deploy a sidecar with all of your services, is almost anything but cloud native. That's sort of designed to take something legacy and move it to the cloud. Whereas if you really want to take advantage of the abilities and the new things that are available to you in the cloud, it does require you to sort of take a step back and choose a new abstraction.
I think people know that lunch is coming after this, so thanks a lot.